Hi everyone, so we're going to go ahead and get started. So hopefully you have had a good morning. We left off on chapter 6, so we'll go ahead and complete chapter 6 PowerPoint notes today, as well as go right into the homework. So I'm going to go ahead and share my screen. So yesterday we talked about this concept with arrow pushing. We talked about this yesterday, but here there are four main ways that electrons move in a polar reaction. You have a nucleophilic attack, loss of a leaving group, proton transfer, and rearrangements. And this is kind of repeating from yesterday. Again, from yesterday, we had this nucleophile. It can attack this electrophile right here. That means it's electron deficient, so it's going to want to accept electrons, so it's electron loving, basically. Here, and this is just a review from yesterday, these first slides. We have this nucleophile right here, have this electrophile. It's moving electrons. You can see, generally what happens then next is this is going to come here, and this is going to be a good leaving group. But for right now, they just want you to know about the main attack, which would be the electrons from the oxygen going into that double bonded that carbonyl group, that C double bonded to the oxygen. Pi bonds can also act as nucleophiles, so it doesn't always have to be, this situation. We can use pi bonds to do that, and they give a good example right here. Loss of a leaving group, I showed you that example right here where the chlorine is going to be a good leaving group. And they're just showing you another example right here where the bromine is going to be a good leaving group. And that's a hydrolytic, so both electrons are going to the bromine. Remember, homolytic would just be one electron here and one electron here, but it's not a homolytic cleavage, it's a hydrolytic cleavage. You can also have the electron density start way up here and kick off that leaving group way down there. And they show you that with the arrow pushing. So this is just a quick review from yesterday. So hopefully this makes more sense today. We did talk about the proton transfer yesterday as well. You can see it right here. So I don't want to spend too much time on it since we did talk about it yesterday. Unless you have any questions on it, then I can go over it again. It says multiple arrows may be necessary to show the complete electron flow. And we see this right here. We see 1, 2, 3 arrows right here. So they're showing multiple arrows showing the electron flow. We can have rearrangements, and we talked about yesterday the hydride rearrangement and the methyl rearrangement. And why did we want to rearrange that? So we can get to a more stable carbocation. And the most stable carbocation is the tertiary carbocation. The methyl one is the least stable. So as you increase the substitution, you see we have 3 sets of substitution. Here is 2, here's 1. The stability increases. So to accomplish that, you can have either a 1,2 hydride shift or a 1,2, and this should be methyl, 1,2 methyl shift. You can see right here, you have an R group, you have an R group, and if you refer back to the previous slide, this would be a secondary carbocation. So you have a secondary versus a tertiary. And what's more stable, the tertiary, so that's why you have that 1,2 methyl shift. And it says shifts can occur. So it doesn't have to occur, but they can occur. So that's a key point. So multi-step reaction mechanisms are a simple combination of one or more of the 4 patterns covered so far. Here we have a proton transfer. Then we have a loss of a leaving group. We get rid of that water. Here we have a secondary carbocation. Now, if we move that methyl group through a 1,2 methyl shift, we'll have a tertiary carbocation. Then we can have a nucleophilic attack. And now we've added that bromine. This is often two other patterns occur in a single mechanism, where you have a nucleophilic attack followed by a subsequent loss of a leaving group simultaneously. It says oftentimes. We're going to talk about when, in some cases, you're going to have the leaving group go off first, and then a second step will have the OH group. But in this case, this is a typical substitution nucleophilic bimolecular reaction where you have it happen at the same time. But let's just say it was more bulky. Now the chlorine's gonna, and let's just say we have a bunch of stuff coming off. That chlorine's gonna leave first, and then the OH is gonna come in. So it's 2 steps right here. But they're not talking about a 2-step process. This is a 1-step, but we will get to this 2-step process in this class. The curved arrow starts on a pair of electrons. So here we have that curved arrow. Here's the curved arrow. It starts with this lone pair of electrons. So we're gonna form a bond and we're gonna break a bond. So at one point in time, this is probably, an alcohol. And now, we have an ether group. So the second arrow shown below is drawn incorrectly. Because the reason why is because they don't have a pair of electrons right there. So the head of a curved arrow shows either the formation of a bond or the formation of a lone pair. Here we see a formation of a lone pair right here. And we see both actually, a bond and a formation, depending on which side you're looking at. The head of a curved arrow can never show carbon forming more than 4 bonds. That's why, we don't just leave it on there like that. We have that going at the same time. Is there any questions on that? Any curved arrow drawn should describe one of the 4 patterns discussed so far. So we have a nucleophilic attack followed by the loss of the leaving group. It says the arrow below is unreasonable. It violates the octet. So because they're not showing you the hydrogens, but you have 2 hydrogens here. If you had that bond go, then we'd have 5 bonds to carbon. So that's why they're saying that wouldn't happen. That would be a violation. So when you encounter a carbocation, you must consider for rearrangement, hydride and methyl shift could result in a more stable carbocation. So, if we have a hydrogen here, could that shift over? And now we have, let me see. a positive here. So would you rather have the positive here or here? Would you rather have a tertiary or a secondary? Well, we know we'd rather prefer the tertiary. And they show it to you in this slide right here, but I showed it to you on the previous slide, so it's the same thing right here. Any questions on a hydride shift then? A tertiary carbocation typically will not rearrange unless a resonance stabilized cation is formed. Here an allylic carbocation is formed. So what they're saying right here is we have this tertiary carbocation, right? And usually you wouldn't think about this rearranging, but in this case it does, because we put the tertiary carbocation right here, we can have this resonance right here. If we have it right there, we can go right here. So something that's resonance stabilized is more stable. So they're both tertiary, all these are tertiary carbons. Here you have a tertiary, here you have a tertiary, here you have a tertiary. But the difference between, the left and the right, on the right-hand side, we have resonance stabilization. And here we have no resonance stabilization. So it's more stable to have resonance stabilization. That's why they moved that that's why there's a 1,2 hydride shift, even though you're not gaining anything as far as the carbocation, you're gaining stability and resonance. As some reactions are drawn as equilibria and others are drawn as irreversible. So here, this is reversible. Two arrows going. So anytime you see two arrows, it's going to be a reversible reaction. Anytime you see one arrow, it's going to be irreversible. But the question comes about reversibility. It's a kinetic and a thermodynamic question. And this is an SN2 attack. I know we haven't talked about that. We are going to talk about SN2, SN1, E1, and E2 at some point in time. That's organic 1 chemistry concepts. But for right now, we'll just say that this will be irreversible. And this bromine, we'll learn, is a great leaving group. So here, water attacks this tertiary carbocation, but yet water is a good leaving group because, water exists on its own, and we know that because that's how life is on the planet Earth. So it is a good leaving group. So it says the reverse process occurs at an appreciable rate. And remember, rates are measured. You can't just say, oh, it's going to happen. You have to actually measure it. Here, this is irreversible. This is a bad leaving group. We are going to learn about leaving groups later on. They're just trying to introduce you to this concept. The reverse reaction does not take place. So think about this. If the reverse reaction did take place, we have this carbanion. We know that carbon wants to have 4 bonds. It doesn't want to exist, in this form. So the reverse reaction is not going to happen. Here they're just reiterating the point that bromine is a good leaving group. Because most of the leaving groups encountered can act as nucleophiles. That means, what does that mean? That means it can come back in here. But generally what you're going to have is something that's going to be something else in there that'll be, more able to take on that, and this will just go away. So that chlorine is going to step in there, and the bromine is, and there's probably protons in the sample, so it's going to have a counter ion, because if you have a negative charge, you have to have a counter ion in there. Because all proton transfers are reversible, but if the pKa difference is 10 units or more, and here we see 15.7 versus 50, it can be considered irreversible. So there's going to be a little bit going back this way, but it's going to be so negligible that it doesn't really count. So in this case, it's going to be irreversible. Here we have a difference between 15.7 and 18. That's why you see the double arrows right there. This carbocation rearrangements are generally irreversible. We can see this right here, from a secondary to a tertiary. Thermodynamically, there is no driving force for a more stable carbocation to rearrange to a less stable one. So what it's saying is, that hydrogen is not going to reshift back here, because then we go to a less stable carbocation. So this is not going to happen. It says reversible. So you have to consider Le Chatelet's principle. So one of the products, N2 gas, is a gas. So N2 gas is the most abundant gas in the atmosphere, and will escape the reaction mixture. That's because it's a gas. So it's going to bubble out. It becomes impossible for reaction to be reversible, because how can it be reversed if this is, you have some type of, you have some type of reaction container. This will be my beaker, and this is in the beaker, and we're producing N2 gas. If it just leaves, well, how is it going to come back to do the reaction? So that's what they're saying right there. You'd have to force it back in. The only way you could force it back in, if you had some type of piston on here, you'd press it back in, and then it could go back in the reversible direction. But if it's out to open atmosphere, then it's not going to happen. That's the end of this PowerPoint slide. So give me a couple minutes I'm going to go ahead and get the homework slides open. So I'll be right back. All right, everyone. So for those listening synchronous and asynchronous, I'm back. If you're listening asynchronous, you didn't even notice the small break, because I just paused the video. So we will continue on with chapter 6 homework. So hopefully you had the opportunity to open up the chapter 6 homework. I'm going to start sharing my screen now. All right, here's chapter 6. And we'll start with question 1. Let me see. There's not too many homework questions on this one. There's only like 16 questions, so we'll get it all done today. And I have no more after this, so once we finish this, we're done for today. So the first question wants you to distinguish basically between a homolytic and a heterolytic. So there's only one barb here, so that's going to be homolytic. And it asks what the product is. Well, when you have, this is called a radical. So product 1 and product 2 are both radicals. So this is also going to form a radical. It'll have CH3, and I'll have a dot right there. And this is reaction A. Now reaction B, this shows a heterolytic bond cleavage. And heterolytic, it's going to have both barbs. So product 3, oh, it's not right. It's not letting me write for some reason. There we go. The product 3 is this, and that's your carbocation. And product 4, which is bromine, that's going to be your inorganic anion. So inorganic anion. So that's your answers for question 1. All right, so we'll go to question 2. Question 2 involves bond enthalpy. So bond breaking and bond forming. Talking about BDEs, bond dissociation energies. BDE stands for bond dissociation energies. So let's see. It gives me a reaction. Step 1, let me see. So the bond broken will be the 423. So we're gonna bust off that. Basically, what we're doing is this is going to be breaking, right? And that's 423. And forming an HCl bond gives us 432. We take our bonds broken minus our bonds formed. So we broke that bond, right? That's 423. Subtract it from 432, and that gives us -9. So let me see what step 2 is. Okay, for step 2, I'll call it S2. We have that chlorine, right? And we're gonna break this bond. You know, we're gonna bust it open. That's 243. So we know we're gonna put 243 here, and this is the bond's broken. Oh, I'll draw that arrow. And what are we gonna form? Well, on the other side, you see we form a CH2 Cl bond, right? And that bond formed is 354. So we take 243 minus 354, and that gives you 111. So the overall is just the sum. So it's the sum, and we can call this step 1 and step 2. So it's the sum of step 1 plus step 2, and step 1 is minus 9. Step 2 is, and this is minus 111. Sorry about that. And this is minus 111, and this equals minus 120. Oh, make that a little better. There we go. So that should show everything there. Any questions on 2? So Q3, here they show you an energy diagram. It goes like this, it comes down. This has a 125 starting point, this starting point right here. It's in increments of 25. So that difference is 100. You know, 125 minus 25 gets you to 100. So now if we go down like this is exothermic. So that difference is 100, but you know, they want to know, you know, what is the heat of reaction? Well, if you start at 25 right here, if you end at 25, so you take 25 minus your starting point, which is 125, that's how you get minus 100. I mean, the difference in the range is 100, but the way they're asking the question, you have to solve it like this. I should just get rid of that, otherwise that might confuse people. Now let's just say it was going this way, then that's endothermic. But we don't have an endothermic reaction, it's exothermic. This would be endothermic the other way. That means this is releasing energy. This would be, it absorbs energy, it needs energy for the reaction to take place. You know, we can think about releasing energy with our combustion engines. Endothermic would be if we're heating a pot of water. That water needs to be heated up if we want to get it to boiling. Let's go to question 4. Let's classify the possible combinations of signs for reactions delta H and delta S by resulting to spontaneity. So delta G equals delta H minus T delta S. So this might help us out. If delta G is negative, it's going to be spontaneous. So we just need to think about how do we get our signs to be spontaneous. So there's 4 different categories: category 1, category 2, category 3, and category 4 across the board, and we're just going to label them like that. So category 1 says spontaneous as written at all temperatures. So if your delta H is negative, well, that's going to make delta G negative. If your delta S is positive, so a negative times a positive is a negative, so that needs to be positive. So spontaneous in reverse, so reverse means opposite. So when they say the reverse, then we have to go the opposite of this. So delta H will now have to become positive and delta S is negative because they're talking about the reverse reaction. Spontaneous as written above a certain temperature. Let me see. So above a certain temperature, delta S will be positive and delta H can be positive. Because think about this. If this is a really high temperature, if T is very high, delta H doesn't matter anymore. I don't really enjoy this question because delta H could still be negative, but as T is very high, delta H becomes negligible. That's why delta H can be positive in this case. So if you go below a certain temperature, delta H needs to be negative because we want to have it spontaneous. And if temperature becomes, close to 0, then delta S can become, negative and it won't matter. Because anything times 0 or minus 0 will still give you a very small number. So that's why this is negative. I don't really like the wording of this question, but that's the thought process. That's 4. Question 5. It wants to know if it's exergonic or something like that. And it's exergonic. Let me see, my pen's not working now. There we go. Question 6. Complete the table relating to values of delta G and K. So delta G equals minus RT natural log of K. So, and they give you different ways to think about it. They put delta G here. If it's less than 0, if it's equal to 0, if it's greater than 0. We kind of have this chart right here. So if delta G is less than 0, and this is K, K has to be greater than 1. And if you just put that in your, your calculator, you'll see that works. And put anything in for R and T. Usually R is 8.314 though. 8.314 times temperature, doesn't matter. Let's make it a negative number and take the natural log of something greater than 1. So let's just say 10, and I get a negative value. If it's 0, K has to be 1 because the natural log of 1 equals 0. So anything times 0 is 0. So that's how that works. And and this one will be easy because this will just be the opposite of this one. And this will be less than 1. That's just opposite. Right, so let's go to question 7. So something like this. This one's green. This one's blue. So we have the reactants. We have the products. So that should be pretty easy to figure out. This is your delta G. This will be your catalyzed. We add a catalyst. This will be uncatalyzed then. Remember, we're looking at the activation energy. And this line right here, and this line right here, be your standard free energy of activation. So EA is what I'll call it. All right, let's go to question 8. They give us this reaction. And they ask us about reaction rates. It tells me that mine are both. So you may have different numbers here, so you have to pay attention to your numbers. 1.40 molar. And my rate equals 0.0050 molar per second. So you may have different numbers here. So if you get a different answer than me, that's okay. Just use the same process. So the rate equals K times the concentration of this stuff times the concentration of sodium hydroxide. And they give us the rate. So they want us to find the rate constant K. So this is your rate constant. So the rate over this stuff equals K. So that's 5 divided by So now that we know the rate constant, we had to figure out the rate constant first to do any of the other stuff. Now I know the rate constant. So if the concentration is doubled, so if CH3Br doubled, then the rate equals the rate constant, which is 0.26 multiplied by this is doubled now. So it'd be 0.28 times the original concentration of sodium hydroxide. And this equals 0.01. 0 molar per second. And I'm gonna have to go on to the next slide because I'm just running out of room, unfortunately. So if sodium hydroxide is halved, we have the rate equals K, which is 0.26 per molar per second times 0.140. That's the original concentration of methyl bromide. And then the half of the sodium hydroxide would be 0.070. I forgot my units in here, so let's add the units. And this is going to be 0.00250 molar per second. That's when this is halved. And if we increase them by a factor of 5, so we're going to go 5x. So you take 5 times 0.140, which is 0.7. Let me, doing that in my head, let me get my calculator out. Yep, that was right. So we have the rate equals 0.26 per molar per second times 0.7 molar. 0.7 molar equals 0.13 moles per second. So here's your 5x. Here's your sodium hydroxide halved, and that's this. And then you have the other one. So I have a thing in the chat. So units for K. Let me go to the previous screen. So these units were, this rate is in molar per second. And here these are in molar. So molar times molar is molar. So I'll just look at the units here. Molar per second. And then you have this was let me see. Then you have molar squared here. So that will cross off, and then you get equals to per second per molar. And that's how you get this right here. Okay, you're welcome. Then let me go to the next slide in case you had any questions about the other two questions. Actually, let me save this because I've had bad luck with I'm gonna stop sharing. I'll reshare it, but I've had some bad luck with the EKU technology. I want to make sure that you guys have this, so that's why I'm saving this right now. We've done 11 questions, or not 11 questions, but 8 questions, and it's a good time to save the work. I should be sharing my screen again. So did everyone get that one? Okay, so I'll go on to the next one. What question was that? That was 8, so we're doing 9 now. Q9. It's just labeling a diagram. Here we have something that looks like this. This is going to be your activation energy, so EA. This will be starting material. So I'm just going to label it starting. This will be products, obviously. This change right here, this is your enthalpy change. I'm going to call it delta H, which delta H is enthalpy, so you should know that. Here you have some intermediates. This is your rate limiting transition state. and here's your non-limiting transition state. And the difference between the rate limiting and the non-limiting is it takes the most energy to overcome. And this is actually a little small. Oh, I didn't want to do that. So we'll try that. Yeah. This step right here it takes more energy to overcome this rate limiting step than the non. So the rate limiting step, you see that right there, it has this difference right here. And we're trying to overcome, it doesn't take as much energy because we've already overcome the initial big step. So that is 9. And 10 we can do on the same slide. There's not much to 10. It says for each compound, determine the direction of polarity. For bromine and bromine, there is no direction because they cancel each other out. For HCl, you're going to go this direction. And for FCH3, you're going to go this direction. So why don't we go ahead, we'll take our 10-minute break right now. We'll come back at 11 o'clock and we'll finish the questions. Right, we're back from our break. We'll start on with question 11. So let me go ahead and share my screen. So question 11 says, analyze the polarity of each bond in this compound. Let me draw it real quick. It says, which bond other than the CC bond is the least polar? This will be the least polar. It says, which carbon atom has the most partial positive? And it'll be this one because you have a partial negative here, partial negative here. So all that electron density, I'll call it ED, is going to concentrate over here. So this is going to be a real big partial positive. So this is going to be the one that has the most partial positive character right here. And that's it for 11. Question 12 says, identify the nucleophilic site in each of the molecules shown. So the nucleophilic site will be A. It's going to be the oxygen atom. So this is going to be the nucleophilic site. And for compound B, so this is compound A. Compound B, it's going to be the nitrogen group. There's going to be a lone pair of electrons here, so you're going to select option C. So it wants us, so question 13, we can put it here. There's not much to it. It has a Cl, and we're going to draw a homolytic cleavage. So we have one barbed here, another barbed here, and that's what you're going to draw. Let me see, this is kind of interesting. Yeah, that's what we'll draw. You may have to, I don't know how they require it. It's all the same thing though. They may want it like this. I have no clue. It's the same thing though. And you're going to be left with, your radicals, your chlorine radicals. So that is a homolytic cleavage. Question 14, we could even draw it right here too. There's not much to this. And that's a chlorine. It wants you to draw the mechanism for this leaving. So this is going to be a good leaving group here. So it's going to leave, and it's going to be this can be a tertiary carbocation followed by your chloride anion. Question 15 wants us to indicate the flow of electrons. So we have this ammonia. That's a lone pair right there. And you have HCl. We're going to have a proton transfer here and then here. And we're going to have that. And 16, I can go ahead and draw this on the same slide too. And this is gonna be it. So we have our carboxylic acid right here. And we're gonna, form these products. So how this will happen, first, this will come here. So this is gonna be your first step. Secondly, then, this bond's gonna break and it's gonna come here. And these electrons are gonna transfer here, and that's how we get this guy right here. So the first, second, and this will third. So that's all 16 questions for chapter 6 homework. So chapter 6 homework will be due on the due date that I haven't achieved. Let me see. So it's due on June 11th. So make sure that you get the homework done by June 11th. There really shouldn't be any excuse. We did the homework today. So you have all day today to finish it, all day tomorrow, and all day Saturday. There's a question. So I will be posting the exam sometime Saturday. I don't know what time on Saturday, but it'll be posted sometime Saturday. I'm hoping to, make the exam by sometime tomorrow. That's my plan. And the exam one will cover everything that we've covered up till now. So that means everything, including chapter 6. So that's a good question. So if you're listening asynchronously, we will cover everything up to and through, up to chapter 6. So that includes chapter 6. And what's going to happen with the exam is, you're going to have a certain amount of time to complete the exam. So, please look in your syllabus and make sure that, and I'm going to send out an email because I'm going to look at the syllabus myself to see, when I have the start date and the due date. So I think according to the syllabus, the exam is supposed to be posted on June 11th. So sometime during the 11th, it'll get posted. And then you'll have, I think I give you till Wednesday, but I just want to double check that for you to complete the exam, and you'll have a certain time period to complete the exam. So I haven't decided how much time yet, but there will be a time period where you'll have to complete the exam within a certain time. All right, so I think I'm going to stop recording. Everyone have a great day, and I will stick around if anyone has any questions. Thank you.